Hi, this is Aaron Jerome at Jerome Electronics. It's time to introduce the basic logic gates. These are the basic gates that are used to, we combine these. It's almost like snapping these together like Legos to create greater and greater intelligence in a machine. So these are the smallest units of intelligence in the electrical computing world. And we're going to talk about these. And so you'll need a summary sheet, and I've given my students a copy of this one. And this actually has places to put different pieces of information about each gate. We're going to be talking about the number on the chip. There's a lot of numbers, but there's a number that we're interested in, the 74XX number. We'll talk about that in a minute. The name of the gate, they all have a name. We're going to explain what each one does. We've already talked quite a bit about the AND gate. We'll be including that in this group. There is a symbol that is used to represent the gate, the schematic symbol for the gate. There's also a Boolean equation that is used to represent the gate. And of course, each gate has a representative truth table. And the truth table is basically a device that is used to convert different kinds of logic combinations into an equation. That will be discussed more in a later video, but for now we need to know what these basic gates are, the smallest unit of artificial intelligence, these basic gates. Okay. Incidentally, later on, I've got another video that talks about how these gates are constructed from transistors. Videos that talk about transistors and how to understand how to read them from the transistors. So anyway, we've got to let's get started on these. Now, these gates, each one has a number, and the first gate is a 7400, but I'm not going to explain that gate first. It's more understandable if I explain that one later. There's the 00, there's actually a 01, but we're going to talk about the 00, the 02, the 04, the 08, the 32, and these last two are going to be the 86 and the 266. Now, it is my intention that my students memorize this sheet to the point where I can give them a copy of this sheet and they can fill in all of the missing information. It's not that hard, and I'm going to explain why it's an easy sheet to memorize, mostly because a lot of patterns exist on this sheet, and went the wrong way. And so keep your eye open for patterns as we talk about the different gates on this sheet. We're going to start with the 7408 for a couple of reasons. First of all, that's kind of a fundamental gate that we always seem to have a need for. The 08. We've talked about it before. I have already explained a few things about it. This gate has a name. We call it the AND gate. Remember, not only are you supposed to write all these words down, but you're supposed to record all of the red stuff as well. I've explained before that the AND gate is a multiplier. That's its job. That's its job, to do logic, to do thinking, to do intelligence. It multiplies. That's what it does. That's its contribution to artificial intelligence. There is a schematic gate symbol that we have. I want you to sketch this gate symbol and notice a similarity. This symbol, the gate itself, has two inputs. It has input A and input B. This gate is shaped like a letter D. And the word AND has a letter D. So the word AND has a symbol in there that looks a whole lot like the schematic symbol for an AND gate. Okay? So basically, A is going to be multiplied against B, and the result will be given as X. Remember, there's only two symbols that go into these. A can be either 0 or 1, and B can either be 0 or 1. And so this is also the Boolean equation, the Boolean algebra equation for it. That's pretty simple to understand. Really, what we're doing is multiplying A times B, and that equals X. Now, this schematic symbol doesn't always have this dot in the middle. I put that in there so that my students can remember that's the multiplier dot, so this gate multiplies. Now, the truth table. What we're doing with the truth table is we've got A and B. Those are the inputs. And what possible inputs could there be? Well, B is going to either be a 0 or a 1. And since A can also be a 0 or a 1, we want every possible combination of 0 and 1 as the inputs. So I'm going to put another 0, 1, 0, 1 here. But the first column changes every one time as we count in binary. The second column to the left is the 2's column. This is the 1's column, so it changes every one time. The next column to the left is the 2's column. That changes every 2 times. And by doing that, we've counted in binary. This is the binary number 0, the binary number 1, the binary number 2, and the binary number 3. These are all inputs, and we're multiplying them together because that's what an AND gate does. It takes A and multiplies B against it, and A times B in the equation. So what we're doing is putting a table of every possible combination of the inputs and also recording what the outputs are. So what's 0 times 0? Well, that's a 0. Can you fill in the rest? 0 times 1? Still 0. 1 times 0? Still 0. The only time you get a 1 on the output is when you get a 1 on both inputs. So 1 times 1 is a 1. Now look at this. This gate is easy to remember because this truth table is easy to remember because all of the truth tables are simply going to be a binary count. So 1's column will be 0, 1, 0, 1. The 2's column will be 0, 0, 1, 1, and they combine to make a 0, a 1, a 2, and a 3. And it's the same for all of these other truth tables, except this 4 gets a little wonky. That's actually easier. So the rest of them, if you can count in binary on all of the truth tables, then you have figured out all of the inputs for all of the other truth tables. The outputs are based on what the logic gate can do, and this one can multiply, so we simply multiply these together to get our results, and we're done with the 7408. The next most fundamental gate is going to be the 32, the 7432. It is known as the OR gate. The OR gate adds. That's what it does. It can add. So the OR gate has a symbol that looks a little bit like the other one, except it's not a letter D. The AND gate is rounded on the right side. The OR gate is pointy. In fact, OR ends with an R. If that were a lowercase r, you could imagine that this shape here is an R. And that would help you remember that an OR gate is shaped a little bit like a lowercase r, but there's more lines. I don't know if that helps or not. But it adds. That's why there's a plus here. That is not normal when we're representing gates, but I like to put them in. It helps my students remember. What we're doing then is we are taking inputs A and B, and we're adding every possible combination of A and B and figuring out the result. The Boolean equation then for this is simply A plus B equals X. If you remember correctly, the truth table has just a binary count on the inputs. The 1's column changes every one time, and the 2's column changes every two times. If we had a 4's column, it would change every four times. If we had an 8's column, it would change every 8. The binary pattern is 1, 2, 4, 8, 16, 32. It doubles every time. When we get into binary counting and binary number systems, you'll see that. But we don't need to worry about that right now. So let's see if this thing holds out. 0 plus 0. Well, that result is 0. 0 plus 1. Well, 0 plus 1, that's a 1, right? 1 plus 0 well, that's also a 1. And 1 plus 1. Okay, this is a little bit different, and we'll explain it more later. But what this is really saying is that anytime we have a 1 and a 1, that's a true, and that's a true, and true plus true is always true. So that's a little bit strange, a little bit hard to understand. We will explain it in more detail later. But just remember that this one is adding until you get to this one, and it's still combining. 1 plus 1 is a 1. And we will also resolve your confusion later, but you kind of have to remember that 1 plus 1 is a 1 because true plus true is a true. Kind of a way to think about it. So anyway, these are the two most used gates, the AND gate, which multiplies, the OR gate, which adds. The next gate is going to be the next most common gate, and it is known as the O4, and it is an inverter, or sometimes called a NOT gate. And we have to be careful when we present this because this flips. What it does is it takes, well, there's only two numbers, a 1 or a 0. So if you put a 1 in, it flips it, and you get a 0 out. If you put a 0 in, it flips it, you get a 1 out. You always get the opposite out of whatever you put in. Okay? Now, I said you have to be careful about this because the gate itself, the gate symbol, always includes a buffer. You see this triangle here? That is not the inverter, not flipper gate. The actual gate is this little circle. A buffer is the triangle, and they are all, well, a NOT gate. Okay, as the signal goes through the wires, it weakens over time, and we like to re-strengthen the signal. And so that's what a buffer does. It sort of amplifies, strengthens, and cleans up the symbol. And we see buffer gates by themselves sometimes, but the combination, really just this little bubble, is the NOT gate. I put a little squiggly in there. They don't usually have squigglies, but that helps me and my students remember that this is an inverter. Whatever you put in is the output of it is the opposite number. So you put a 1 in, you get a 0 out, or a NOT 1. You put a 0 in and you get a 1 out, which is a NOT 0. The little line above the A is a symbol that means not rather than is. Okay, so the Boolean equation for this is simply A equals not A. Whatever you put in, you get the opposite out. And since there's only two symbols in binary, 0 and 1, whenever you put a 1 in, you get a 0 out. Whenever you put a 0 in, you get a 1 out. It's a flipper. It's an inverter. It's a NOT gate. I told you the truth tables are they're always numbered in binary, but this only has A as an input, a single input, and only one out. Well, A is the only input, but A can be a 0 or a 1. There is no B, so we're ignoring that. And if you put a 0 in, you're going to get a 1 out. If you put a 1 in, you're going to get a 0 out. So that is all there is to the truth table. The inputs are the opposites of the outputs. With these three gates, you can make all the other gates. And the reason we didn't start with 0, 0, we started with 0, 8, 32, and then 04. The reason we didn't start with 0, 0 is because it's more understandable if you think of it this way. So now we're going to the 0, 0 gate. This gate name is NAND. It's basically a AND gate with a NOT gate on the outside. So a knotted AND gate. What does this thing do? Well, it multiplies first, then it flips. The gate symbol, because it's an AND gate, is identical to the AND gate symbol, except that it has the little tiny bubble there for the NOT gate. Remember I said it's the little bubble that's the NOT gate, and this particular gate has the little bubble on the output, so it multiplies A times B. Its result might be right here, but then it flips the answer over to the opposite, and we call that a NAND gate. The Boolean for a NAND gate is exactly the same as for an AND gate, except it's got the big long not over it. Now, the big long not implies that everything under it has been inverted after what's under it has been done. So the multiplication occurs first, then the answer is given before the not gate, and then the whole result is flipped over to its opposite. If it came out as a 1, it becomes a 0. If it came out as a 0, it becomes a 1. The truth table. With the truth table, we're just doing a binary count. The ones column changes every one time. The twos column changes every twos time. I said the inputs are always the same. All we're doing is making sure we have every combination of A and B possible. There are only 4. And now we're going to multiply these together, and whatever the answer is, we're going to flip it over to the other. So 0 times 0 is 0, but we have to flip that. That means it's a 1. That's what this gate does. What is 0 times 1? Well, that's 0. Flip that over. That's a 1. What's 1 times 0? Well, that's 0. We flip that over. That's a 1. What's 1 times 1? That's 1. And then we flip it over. That's a 0. So if you look at the truth table for the NAND gate and the truth table for the AND gate, the outputs are just opposites of each other. The AND gate would be 0, 0, 0, 1, and these are just the inverted outputs. The OR gate and the NOR gate are also very similar. This O2 is going to be a NOR gate. And the NOR gate, well, it adds first, then it flips. The symbol for the OR gate is exactly the same as the symbol for the other OR gate, except that it has a little NOT gate bubble on the output from the NOT gate. There it is. It adds first, then whatever the answer it gets right here, it flips that over to the opposite answer. The equation for the NOR gate is exactly the same as the equation for the OR gate, but it has this line that says everything is flipped over at the end. The inputs for the OR gate are a binary count. So a 0, 1 changes every single time, and then this is the twos column, so that changes every 2 times. So this is a binary 0, a 1, a 2, and a 3. Now we're going to add these two together and then list the opposite of the results. So 0 plus 0 is 0, so the opposite of 0 is a 1. 0 plus 1 is a 1. But the opposite of that is a 0. 1 plus 0 is a 1. But the opposite of that is a 0. And 1 plus 1, well, remember, true plus true is true. That's the way you have to think about it. And we'll explain more later. And I know it's confusing, but 1 plus 1 is going to be 1. But flip that over, and that is also a 0. The output of the NOR gate is exactly opposite as the output of the OR gate. Okay, so hopefully these make sense. We have now talked about 5 gates: the 0, 0, the 0, 2, the 0, 4, the 0, 8, the 32, and now we've got these two. These two are also variations of the OR gate. More gates that you need to know. These are 7 gates that we need to know. And if there was an 8th gate, we'd call that the buffer gate, the triangle by itself, the amplifier, the signal clarifier, the restorer, but we'll talk more about that later. Okay, so the 86 is a special variation of the OR gate called the exclusive OR, or the XOR, or I like to call it the XOR gate, but I'm wrong and don't do that. It's the exclusive OR, or the XOR gate. What does it do? Well, if there are ever opposites in the truth table, they equal a 1. If there are ever opposites in the truth table, they will equal a 1. And I'll get to that when I get to the truth table over here. The equation is very similar to, or not the equation, the gate symbol is very similar to an OR gate symbol, except that it has an extra echo here, and the plus here has a circle around it. Okay, those are the two differences that you need to know. A XOR or an XOR gate has a little extra echo of the input curve, and the plus has a circle around it. The Boolean equation is this: A XOR B, okay, and it equals X. Now what that means is whenever A is the opposite of B, then the output is going to be a 1. For the truth table, we're going to put our inputs in there, just like we always do. You probably have already done that if you're working ahead of me. And now we're going to look at the inputs. A and B, are they opposites? No. Well, if they were opposites, the output would be a 1, but they're not, so that means the output is a 0. Next row, A, B, are they opposites? Yes, they are. That means the output will be a 1. The next row, are these opposites? Yes, they are. That means the output will be a 1. These two, are they opposites? No. So the output will be a 0. Notice that the only difference between an OR gate and a truth table, or the truth table for an OR gate and a truth table for an XOR gate, is this last one. It's exclusively an OR because it excludes anything that is same-o in the beginning, any inputs that are the same. Only opposites get to have outputs of 1. Very useful gate, used a lot. We will use it in a calculator that we hope to make very soon. And let's do the last one. This next one is another variation of OR. You could probably guess what it is. It's going to be a knotted version of the XOR gate. That means it's all going to be the same, except the output here is going to have a bubble, meaning that all of these outputs are going to be flipped on this truth table. This is called the XNOR gate, the exclusive knotted OR gate, and it means sames equal 1 in the truth table. It has the exact same gate symbol, gate schematic symbol, as the XOR, except for the little bubble on the output. Other than that, they are the same. All we're doing is taking an XOR and inverting the output. The equation is the Boolean equation is exactly the same because it's just the A opposite of B, and then we flip the output in the end. I'm going to populate the inputs of the truth table. I've said enough about that. There's the inputs of the truth table. Now, I have to check if the inputs are sames, then the output is a 1. If they're not the sames, then the output is a 0. These two are not the same, the output is a 0. These two are the same, the output is a 1. And if you look at these outputs, you can see that they are the exact opposite of these outputs because all we've done is taken this thing and then flipped over each one of the output values. Okay, so those are the basic gates that you need to know. Hopefully you have filled out your paper that has all of this information. We're going to try to do a few of these, try to figure these out. But before I go, I want to talk about the patterns real quick again. This symbol looks like a D, just like AND. This one is curved and then pointy on the other side. That's the OR, and that is true for all of the variations of the OR. This one that's knotted, and this one that is exclusive, and this one that is an inverted knotted exclusive. Okay. And this one, that's the triangle. And if you can remember these three, you can derive the other 4 from them. Because, you know, this AND gate is exactly the same as the NAND gate, except that it flips, inverts the output of a regular AND gate. The OR gate and the NOR gate are also very similar, except that, they're inverted. The NOR gate inverts It inverts. It adds first, then it flips. This one only adds. This one adds first, then flips. And so this output is different than this output, completely exactly opposite. Again, the equations are pretty much all the same. This equation is the same as this equation, except this has a line because it inverts. This equation is the same as this one, except that it is exclusively opposites. So we circle this, and this is exclusively opposites, but the result is flipped. And so if you pay attention to what we've just said, a lot of information here, but really, how are you going to remember all of this? Well, the only real way to remember this group of artificial intelligence gates is to practice on a blank sheet of paper like this. See how much you can fill it in, time yourself, then check to see how you did, study it a little bit, try it again. I know that if you try this, just make yourself 10 blank copies, fill it in 10 times, trying to get a little faster and a little better each time, and you will own this information. This information is probably the most important information that you could memorize in this class, more important than all the goat stories, more important than the math that we've done before, although that's all important. This is used from now on. You must understand when I say, what is that gate? And I point to one of these. You have to recognize right away that's an AND gate and it multiplies. What is this thing? It's a XOR gate, and its job is to give outputs that are ones whenever the inputs are opposites. To understand this, you don't have to just stare at it and hope you'll remember it. You actually have to try several blanks. And so it wouldn't hurt to make a copy of blanks. If you're my student, I will give you in Canvas a copy of the blanks, and then you can print as many as you want and practice as much as you want. So we'll even probably practice this 2 or 3 times in the classroom, see if we can get this down, because this is so important to know this chart. Okay, that's it for now. Talk to you next time. This is Aaron Jerome, Jerome Electronics. Later.